This is the 25th lecture on DSP, and our topic today is continuation of analog filter design, and we shall also introduce today transformations from low pass to all other kinds of filters. In the last lecture we talked about Butterworth, determination of Butterworth order, Chebyshev filters, their pole locations, the type of factors that they have in the denominator, and in the numerator you have to adjust. You have to use a factor 1 by square root of 1 plus epsilon squared if the order is even. No such factor is needed if the order is odd. And the orders were found out from a relationship which for Butterworth and Chebyshev are very similar. One uses log and the other uses cos inverse. For the Butterworth filter it is log 10 of square root of 1 by delta s squared minus 1 divided by 1 by delta p squared minus 1 divided by log 10 of omega s by omega p. This ratio omega s by omega p is sometimes denoted as the transition ratio. Obviously, it is a transition between pass band edge to stop band edge. It is also called transition ratio. There are several other terms which have been used, but you can ignore them. Whereas for the Chebyshev n sub c, all that changes is cos inverse replaces log 10. Cos inverse of omega s by omega p, and the numerator is the same. I also told you that if cos inverse tables are not available, which usually are not, you may have to use a handbook, or you use the alternative that in the edge of the stop band 1 plus epsilon squared Cn squared omega s divided by omega p should be equal to delta s squared. But as you know, capital N found from this relationship may or may not be an integer, all right. That is why there is a inequality sign here. So, we should write this as less than equal to or greater than equal to, less than equal to. The transmission at omega s should be less than or equal to delta s, and since this is a squared, it is delta s squared. And this gives you, on simplification, the relationship that Cn squared omega s divided by omega p should be greater than equal to 1 by delta s squared minus 1. Agreed? I simply take the reciprocal, pardon me, multiplied by 1 by epsilon squared, that is right. And therefore, Cn of omega s by omega p should be greater than equal to 1 by epsilon square root of 1 by delta s squared minus 1. The right hand side is known. The transition ratio omega s by omega p is also known. Therefore, one can do it by trial and error. That is, guess, estimate a value of capital N and then find out the relationship between the left hand side and the right hand side, and increment n till the inequality is satisfied. Now, in this calculation one has to be very careful. Suppose the inequality sign is satisfied critically, if both the sides are equal, for example, all right, then you look at it with suspicion. You increase the accuracy of your computation. you increase the accuracy of your computation and look at it with a magnifying glass and see if the inequality is exactly satisfied or not. If not, then you increment by 1, all right. If it is exactly satisfied, then the the lab construction, the hardware construction will take care that it is not satisfied. So, even if exactly satisfied, you increment to be on the safe side by 1, because you are not doing any harm, you are only increasing the cost incrementally. If the filter had cost you rupees 100, maybe another 10 rupees will be added to it. So, it is not a problem. Now, this procedure of trial and error succeeds only if capital N is not very large. Otherwise, it can become very laborious, because you shall have to calculate Cn of omega s by omega p at a large number of capital N's. This you can do by recurrence relation. You know the recurrence relation, Cn of x equal to etc. But then it becomes laborious. One of the alternatives is, the third alternative is to use the relationship cos inverse y equal to log of y plus square root of y squared minus 1. The proof of this relationship is extremely simple. If this is equal to theta, then obviously y equal to cos theta, agreed. If you denote cos inverse y as equal to theta, then y is cos theta, and cos squared theta minus 1 is sin squared theta, and therefore, this will be cos and this will be sin. Cos and sin added together gives e to the power theta, and log of e to the power theta is theta. So, it is a very simple proof. It is sometimes expedient to use this relation. So, you shall have to use this in both the numerator and denominator. The only thing is, it is denominator is simply well, that is also a cos inverse, isn't it? And if you take the ratio, then you do not have to use log natural either, you can use log 10, agreed. So, these are the tricks in the calculation. I have given you 3 methods, whichever is suitable, convenient, you adopt that. For large orders, one invariably uses this, because for large orders you may not get the cos inverse values tabulated at sufficiently narrow intervals, all right. Okay. Now, we start with some examples. Example 1 of Chebyshev filter approximation. Suppose our specs are, I am drawing it on an exaggerated scale, this is 1 and this is 0.8, this is 1 kilohertz and the transition ratio is 5. In other words, the stop band starts at 5 kilohertz and the stop band attenuation must be, stop band transmission must be less than or equal to 0.2. All right. You are required to find out the Chebyshev transfer function. The first thing you do is calculate epsilon. This is magnitude and this is frequency in hertz, okay, not capital omega, not radians. Now, 1 by square root of 1 plus epsilon squared, if this is to be Chebyshev, then this must be equal to 0.8, agreed. So, epsilon from here calculates out as 3/4 or 0.75. Wherever possible, you maintain a fraction, because fraction does not truncate the number. All right, we have found out epsilon. So, the next thing, let us use this relation, that is Cn squared or Cn of omega s by omega p should be equal to 1 over, should be greater than equal to 1 over epsilon square root of 1 by delta S squared minus 1, the relationship that we have just established. Now, delta S 1 by epsilon is 4 by 3 and square root of delta S is 0.2, so it would be 24. 1 by 0.2 is 5, 25 minus 1, 24, and that is equal to 128 by, no, that is equal to 6.532, my calculation. The right hand side is equal to this, all right. So, you start finding for capital, substitute capital N and try a few values. If Cn omega S by omega p here is 5. Now, C1 of 5 is 5, right, and it is obvious that 2 capital N equal to 2 will satisfy. C2 of 5 is 2x squared, 2 times 5 squared minus 1, that is equal to 49, and therefore capital N equal to 2. And with 49, C2 of 5 equal to 49, obviously the stop band will be much over satisfied from 5 to 49, okay, it will be, but there is no other way, okay. If capital N is equal to 2, then you can immediately write H A of S, that would be equal to, capital N is 2, so the denominator would be simply a quadratic, S squared plus B1 omega p is 2 pi times 10 to the power 3, not 10 to the 3, it is radian, you must remember this, S plus C1 omega p squared, and the numerator would be simply C1 omega p squared. Capital N is even, and therefore you must have this ratio 1 by square root 1 plus epsilon squared. For finding out B1 and C1, everything else is known. B1 and C1, you have to find out Y2 first, capital N equal to 2, then B1 and then C1, no C0, okay. Here C0 is the same as Y2, but you have to calculate this in these steps. I have not done so, you can do it. The formulas I have already given you. Let us take another. To bring variety into experience, now we take a more practical spec, that is in decibel. The pass band tolerance is minus 1 decibel tolerance, and the pass band extends to 1 kilohertz. I beg your pardon, what was the transition ratio? I took it at 5 kilohertz, is it? It's not okay. My calculations are wrong. Oh, if it is 5, it doesn't matter. Yeah, okay, it's okay. I go back. I actually made a mistake. I wanted to take 4 kilohertz, but it's okay. With 5 kilohertz, we have satisfied this. Omega S by omega p occurs only in Cn, and therefore we have not made a mistake. Who said I am right? Very good, Arpita, very good. I want your support all the time. The other example, 0 minus 1, and then we have again 5 kilohertz, let us say 5 kilohertz, and the attenuation must be at least minus 40 decibel, magnitude in decibel. So, the first thing you do is to find out, delta p and delta s. Delta p would be equal to 10 to the power, if you remember, minus 1 by 20, and that comes out as 0.8912. Please do verify, these are my calculations. And what we need is not delta p, we need 1 by delta p squared. So let us calculate this at the same go, and this comes as 1.259. My calculations are all with my calculator Casio. Delta S is 10 to the power minus 40 by 20, so it is 10 to the power minus 2. So 1 by delta S squared is equal to 10 to the power 4. All right. So my now it is interesting to find out what order of Butterworth will satisfy these specifications. Then we shall be able to compare Butterworth and Chebyshev. If I want to satisfy the specs by Butterworth, then NB has to be greater than equal to log 10 of square root 10 to the power 4 minus 1 divided by, what was 1 by delta p? 1.259. So it will be simply 0.259. 0.259 and divided by log 10 of 5. This quantity calculates out to 1, let me use a different color. This quantity we shall need it for Chebyshev also. So let us calculate this as 196.5 in my calculator. So n sub b should be greater than equal to log 10 196.5 divided by log 10 5, and this is exactly equal to 3.28. Therefore, n sub b is equal to 4. Okay. You can take some liberties in this calculation, but this liberty should not be abused. In other words, if you had got a number which is 2.99 by making approximation, for example, in this calculation I ignored 1 which is 10 to the power 4, I think you should admit that, right? This would not make a drastic difference here. Anyway, so n sub b is 4, and you know what the transfer function is. H b of s shall be now s squared plus b1 omega c. You have to calculate this. Okay. In Butterworth there is another complication, you have to calculate omega sub c, because omega p is given at minus 1 dB. What is omega c at which the attenuation is minus 3 decibels, you will have to find out. So b1 omega c s plus omega c squared and s squared plus b2 omega c s plus omega c squared. The numerator would be simply omega c to the power 4, and b1 is twice sine etc., etc. b1 and b2 you can calculate. Now let's see Chebyshev. N sub c should be greater than equal to cos inverse 196.5 divided by cos inverse of 5. If instead of using this we use the formula Cn of 5, transition ratio is 5, greater than equal to 1 by epsilon. Oh, we did not calculate, did we calculate epsilon? Oh, we did not calculate epsilon. How come? I should have calculated epsilon, otherwise I cannot find out. Oh, epsilon, my calculation. How do you find out epsilon? Delta S is equal to 1 by square root, not delta S, delta P is equal to 1 by square root epsilon squared. Epsilon I find out approximately as 0.51. Do not take this liberty, go further. I verified that doing this liberty it does not affect the result, because it is an inequality. So Cn of 5 would be again 10 to the power 4 minus 1, I approximated by 10 to the 4. So I get 100 divided by 0.51. which is equal to 196.51. Now we start with C2. C2 of 5, C1 of 5 is 5, so no question. C2 of 5 is 49, that does not do it. C3 of 5 is, either you can use multiple angle formula or the recurrence relation, that is twice x is 5, then C2 of 5 49 minus C1 of 5, which is 5, and obviously this is greater than 196.51. You do not even have to calculate this. Okay, 490 minus 5, 485. So you can do this. Therefore, the Butterworth, compared to the Butterworth, Chebyshev uses a lower order, third order, and it reduces the cost. That is, for the same specs, Butterworth, they can also be identical. They can also be identical. The same order is possible, but in this particular case, the specifications are such that a lower order Chebyshev does the job. And once you know n sub c, then you can write down h c of s as equal to s plus omega, no, C0 omega p, agreed. For a Chebyshev you require a factor C0, then s squared plus b1 omega p s plus c1 omega p squared, all right, third order. So that is enough, and the numerator would be omega p cubed C0 C1. No factor involving epsilon is needed because the DC value is 1. For odd order, the magnitude starts from 1, and you can calculate C0 is Y3. So you calculate Y3, you calculate B1, you calculate C1, and you have obtained what you wanted. All right. Now we go to transformations.
So,
yes.
if Butterworth and Chebyshev filters have both have the same orders, then which one to prefer?
We will prefer Chebyshev. Chebyshev is always preferred. Okay, we will prefer Chebyshev because the cutoff slope shall be different. Chebyshev will have a better cutoff slope than Butterworth. But if you want to keep life simple, then you do not even think of Chebyshev, you design a Butterworth and do the job. If it is 1 or 2 filters for a dedicated job, it does not matter. But in an industry, they never fabricate 1 or 2 filters because it requires a lot of engineer time to design a particular filter, and therefore they produce in thousands, if not 100,000s. Okay. Any other question? We next considered frequency transformations in analog filters. What we wish to do is to transform a low pass filter, a normalized low pass filter, that is, normalization is with respect to frequency. Normalization with magnitude, of course we do, we always do, irrespective of analog, digital, whatever it is, and this is delta p. Then we have omega s, we normalize the cutoff frequency to 1. Okay. So, this is what we mean by a normalized low pass filter. Normalized low pass filter has a cutoff frequency of 1. This cutoff frequency could be the 3 dB frequency for a Butterworth, or it could be 1 dB frequency for a Butterworth. It could be 0.5 dB for Chebyshev, whatever it is, our pass band is specified from 0 to 1, okay, capital omega 0 to 1. We want to transform this filter into other kinds of filters. For example, if we wish to transform this to another low pass filter whose cutoff frequency is omega p instead of 1, then what we do is simply substitute S by S divided by omega p, correct? Now, fortunately, in low pass to low pass we can keep the variables the same, okay, variables the same, that is small s here and small s by omega p there. Now, if I convert this to omega p radians per second, then obviously the stop band will start from omega s multiplied by omega p. So, this is frequency denormalization. So, what I want to convert is a normalized low pass filter NLP to denormalized other kind of filter OKF. Okay? I want to design an actual filter with actual specifications starting from a normalized low pass filter. First, we have to see how a normalized low pass filter can be transformed to a denormalized other kind of filter, and in order to keep the symbols tractable, we shall use capital S as the complex frequency variable for the normalized low pass filter, and small s, please distinguish between them, small s, the first letter of my signature I always write like this to emphasize the fact that you should distinguish between capital S and small s. So, normalized low pass filter would be small s and denormalized other kind of filter would be capital S, and therefore, if we go from normalized low pass filter to denormalized low pass filter, then we shall replace capital S by small s divided by omega p. Agreed? That is all we will do. Capital S, for example, if I have a first order Butterworth filter, first order Butterworth or Chebyshev or any other first order, only one kind of filter is possible, 1 by S plus 1 having a cutoff frequency at 1 radian per second, 3 dB cutoff, and if we want a cutoff of omega p, then the denormalized low pass filter would be 1 by S by omega p plus 1, which is equal to omega p divided by S plus omega p. Indeed, it is a first order filter with a cutoff frequency at omega p. All right. Now, things are not that simple when you go to other kinds of filters. For example, let's consider from low pass, denormalized low pass to high pass, NLP to denormalized HP, all right. Then capital S has to be replaced by omega p divided by S, all right. This is the transformation. Why this, what is the justification of this transformation? You can see capital S equal to omega p divided by S. So, capital S equal to 0 corresponds to small s equal to infinity. In other words, a low pass filter has gone to a high pass filter. Not only that, capital S equal to plus j 1, which is its cutoff frequency, normalized low pass, this goes to small s is equal to minus j omega p. Now, capital S equal to minus j 1 corresponds to S equal to plus j omega p. All right. So, you see the magnitude characteristic is even. If you plot for negative frequencies, you shall get the even. So, s equal to plus j1 leads to small s equal to minus j omega p, which means that the cutoff frequency is omega p, and it is now a high pass filter. Capital S equal to infinity, where the low pass filter has 0 characteristic, 0 magnitude, corresponds to small s equal to 0, and therefore we have simply flipped over. Omega p is our pivot, and we have flipped over the characteristic. For example, if I have a normalized low pass first order low pass filter 1 by capital S plus 1, then replacing capital S by omega p by S plus 1 gives me S divided by S plus omega p, which is obviously a high pass filter. Okay? I am doing it from various angles, so that you are convinced that this transformation is indeed correct. The positive frequencies here go to negative frequencies, it is not a matter of concern, because if s equal to plus j gives small s equal to minus j omega p, s equal to minus j1 gives you the positive frequency. All we are interested in the magnitude characteristic, frequencies between 0 and infinity. Okay? So, if I can find out the corresponding frequency positive or negative, I know the other one must also be there. Now comes the question of a band pass filter, that is, we want to convert a normalized low pass filter to a denormalized band pass filter. Then we shall replace capital S by a constant q multiplied by small s squared plus omega 0 squared divided by omega 0 s. First let us see whether it is a band pass filter or not. Capital S equal to 0, where the magnitude of the low pass filter is unity, okay, unity for a Butterworth filter, not necessarily for Chebyshev it may be different, but it does not matter. A capital S equal to 0 corresponds to small s equal to plus minus j omega naught, and therefore whatever transmission I have at DC for the low pass filter transfers to a non-zero finite frequency omega 0, all right, and capital S equal to 0, I beg your pardon, not 0, capital S equal to infinity is possible in two ways. One is small s can go to 0 or infinity. In other words, at both DC and infinite frequency, the characteristic of the low pass filter at S equal to infinity is reproduced. Low pass filter at infinite frequency should give 0 transmission, and therefore, if my low pass filter was like this, the corresponding filter here shall be like this, maximum or equal ripple, whatever it is. If it is even equal ripple, then it shall be a minimum here, but it shall remain within the pass band. Okay? So, this is omega 0, and at 0 it is 0, at infinite frequency it is 0. If this is the filter, obviously it is monotonic, and my characteristic is quite okay. All right. Now, what happens to the cutoff frequency? Now, you are convinced that this is indeed a band pass, low pass to band pass transformation. What happens to the cutoff frequency? When cutoff frequency corresponds to capital S equal to plus minus j. Let us take the plus sign, we will derive the other results very simply. Then capital S equal to plus j will correspond to q s squared plus omega naught squared divided by omega naught s equal to j. In other words, s squared plus omega naught squared minus j omega 0 s divided by q is equal to 0. This is a quadratic equation, and therefore, there are two solutions of this, and the solutions are, if you solve them, you get j omega 0 divided by 2q. You can put it in this form. I skip the algebra. 1 plus minus square root of 1 plus 4 q squared. This is what we get. All right. There are two solutions. Obviously, one of them is positive and the other is negative, because 1 plus 4 q squared is definitely greater than 1. Okay. And similarly, if you take s equal to minus j1, then the solution would be j omega 0 divided by 2q. Instead of plus 1 here, we shall get a minus 1, because this will come with a positive sign now. Agreed? So, we shall get minus 1 plus minus square root of 1 plus 4 q squared. What does this mean? It means that there are 4 solutions. S equal to plus minus j1 goes over to the band pass filter to 4 frequencies, but then 2 of them are positive, 2 of them are negative. We are interested in the positive frequencies, and you see, if you take a plus sign here, it will be positive, and if you take a plus sign here, it will be positive, but then this solution would be lower than the first solution, isn't it? This is 1 plus this, and this is minus 1 plus this, and therefore, the two cutoff frequencies s equal to j1 goes over to small s equal to plus minus j omega 1 2, where the cutoff frequencies are omega 1 would be equal to omega 0 divided by 2q square root of 1 plus 4 q squared minus 1, okay, and the other one would be omega 2 equal to omega 0 by 2q square root of 1 plus 4 q squared plus 1. Agreed? The other two solutions are minus omega 1 and minus omega 2. Okay?
So this means that the mapping is not 1 to 1.
The mapping of what?
Mapping of that one particular frequency.
Mapping of the, yes, correct, correct, that is a good question. What he says is that the mapping is not 1 to 1. Well, what is the nature of the transformation? It is not a linear transformation, it is a quadratic transformation. So, every s value here shall have 2 corresponding values. It is not a 1 to 1, but as far as the magnitude characteristic is concerned, 1 radian per second will correspond to 2 frequencies, capital omega 1 and capital omega t. And this statement, this result is unique. It cannot be any other frequency. Okay, but the interesting thing is that the product of the two is omega naught squared. In other words, the two frequencies, the two passband edges of the band pass filter have geometric symmetry with regard to the center frequency omega 0, all right, and omega 2 minus omega 1, which is the bandwidth, we shall call this capital B, is simply equal to omega 0 divided by q. The bandwidth excuse me, the bandwidth is omega 0 by q, and if you remember the definition of q, it is quite computable. What is q? Q is center frequency divided by bandwidth. Okay, so everything fits in place. The only problem is the the two frequencies are not in arithmetic symmetry, they are in geometric symmetry. And in fact, this geometric symmetry also reflects in the characteristic all through. In other words, this creates a problem at a later point, so therefore one must understand this. The characteristic is not symmetrical, is not arithmetically symmetrical. That is, if the shape is like this, it should have come like this, but it does not. Okay? And if you take any level, let us say delta, then there are two frequencies, let us say omega S1 and omega S2. These are also geometrically symmetrical with respect to the center frequency. That is, any level, it does not matter what level it is, 3 dB or 1 dB cutoff or 5 dB, this is arbitrary, and any two frequencies on two sides at which the transmission is the same will be geometrically symmetrical. That would be equal to omega naught squared. And delta, I have used a symbol S intentionally. If this is the stop band spec delta S, all right, then the stop band frequencies shall also be geometrically symmetrical. In other words, omega P1, what we called omega 1 earlier, is actually the edge of the pass band, okay, first edge. The second edge is omega P2, this is also equal to omega naught squared. In other words, your specs must be such, specs on the band pass filter must be such that omega S1, omega S2 is equal to omega P1, omega P2. Now, you cannot you cannot compel your consumer to make such a specification. He makes specifications according to what is required. Then it is the duty of the filter designer to satisfy the specs, but since the tool in his hand, the transformation gives geometric symmetry, he must modify these specs, and this is where the important point comes. Whatever specs are given, he must modify these specs such that the pass band is exactly satisfied, it is sacred, and you play with the stop band, that is, modify in such a manner that geometric symmetry is satisfied and the stop band is over satisfied. This is the point that I wish to emphasize a little later, but let us get some experience of this normalized low pass to band pass filter. Suppose I take the first order filter and replace capital S by H B of S. B now stands for band pass, BP, band pass. So, I will get what was the transformation? Q S squared plus omega naught squared divided by omega naught S plus 1. Okay. You see, the order is doubled. From first order you go to second order, because the transformation is a biquadratic function. It is a second order transformation. You cannot make a first order band pass filter. Any first order filter is simply either capital S by S plus 1 or 1 by S plus 1. You cannot make a first order band pass. It is only second order. If I simplify this, then I shall get omega 0 S divided by S squared plus omega naught squared Q plus omega naught S, and if I divide by Q, then I get omega 0 by QS divided by S squared plus omega 0 by QS plus omega naught squared. This is second order band pass filter. At small s equal to 0, the magnitude is 0, small s equal to infinity, magnitude is 0, and small s equal to plus minus j omega naught, the magnitude would be 1. When S squared plus omega naught squared is 0, the magnitude will be 1, and you can find out the two cutoff frequencies 3 dB or whatever dB it is. But it is interesting to note what is omega 0 by q, is that the bandwidth? Omega 0 by q is the bandwidth. Okay. So, why do not we write this as h BPS as equal to Bs divided by s squared plus Bs plus omega naught squared. Let us divide by Bs, okay. Then I get 1 plus 1 over Bs s square plus omega naught squared. That is equal to, if I take the variable on the complex on the imaginary axis, HBP of j omega would be 1 by 1 plus 1 over b, I take s inside, then I get j omega minus omega 0 squared by omega. J will come out. Can I do that? J comes out, s plus omega naught squared by, okay, okay. So, I take 1 by, minus sign comes because 1 by s, and that is 1 by, that is j omega. So, j goes up. So, you get 1 plus j, let us take omega 0 also out. I am writing it in a particular form. Then I can write this as omega by omega 0 minus omega 0 by omega. Agree? What is omega 0 by b? That is the q. Okay. So, my expression now simplifies to, I am going back and forth between omega 0 q and b, so that these three terms relationship gets imprinted in your mind. So, I get h bp j omega magnitude squared can be written as 1 by 1 plus q squared omega by omega 0 minus omega 0 by omega whole squared. If you take any frequency, let us say omega s1 and another frequency which is omega naught squared by omega s1, then you see the magnitudes should be equal, isn't that right? Omega s1 by omega 0 and omega 0 by omega s1. If you put omega s2, then you get omega s2 by omega 0 minus again omega 0 by omega s2, and they should be identical. Is that clear? Is this okay? The two frequencies which are related by this relation, that is omega s1 omega s2 equal to omega 0 squared, the magnitude is the same, all right, which also demonstrates geometric symmetry. The magnitude is the same. This is another way of saying the thing, that one of them was that at the same attenuation, the two frequencies are geometrically symmetrical with regard to omega 0. Here we prove by an example. This is no proof, but it is only to demonstrate that if the frequencies are geometrically symmetrical with respect to omega 0, then the magnitude should be the same, okay, and this does create problems. But before we consider the problem, let us complete this list from normalized low pass to denormalized band stop filter. And the transformation here is simply the reciprocal of the low pass to band pass transformation, simply the reciprocal. In other words, we shall have q s squared plus omega naught squared and omega naught s. That is it. That it is so can be very easily shown by considering these typical points. Capital S equal to 0 corresponds to small s equal to 0 or infinity, and therefore, if it is a Butterworth filter, unity magnitude at capital S equal to 0 is transferred to the denormalized filter to 0 and infinite frequency, and therefore, our job is done. In between there must be a minimum, and that minimum you can see that when capital S equal to infinity, small s is equal to plus minus j omega 0. Now, capital S equal to infinity, for a low pass filter the transmission should be 0, and therefore, at omega naught it must come down to 0, and we have got a band stop filter. Okay. The pass band edges, again for the same transmission, these what do we call them, omega 1 and omega 2. If this is delta p, you see there are two pass bands now and one stop band. Unlike the band pass filter, it is just the complement of the band pass filter. There are two pass bands, and omega 1 and omega 2 by the same token is very easily shown that this is also equal to omega naught squared. Similarly, the stop band specs delta s, okay, delta s, these two frequencies omega s1 and omega s2, it has become too complicated. Let me draw it separately. I want this picture to remain in your mind. This is 1, this is delta p, and this is delta s, and the corresponding frequencies are omega p1, omega p2, this is omega s1, and this is omega s2, and the center frequency is omega naught. Okay. Center frequency means the frequency of null transmission now, and the center, the word center has also to be taken with a pinch of salt. Why? Because it is not arithmetically symmetrical, it is centered in the geometrical sense, geometric symmetry, and here also by the same procedure you can show that this must be satisfied, equal to omega naught squared. Omega naught is now the null frequency. As an example, if you want to design a 6th order Butterworth band pass filter, 6th order Butterworth band pass filter, then you will start with 3rd order Butterworth low pass filter, normalized low pass filter, and you know what the transfer function is, s plus 1 s squared plus s plus 1. All that you have to do now, if you know the specifications of the band pass filter, then you have to do now is to replace capital S by s squared plus omega naught squared, what was it, divided by omega 0 s q times this. All that you have to do is this. Okay. But to be able to design, mark this carefully, to be able to design the normalized low pass filter, you see, given the normalized low pass filter, we can always go to the band pass or band stop or high pass filter, and whatever frequencies come, we shall have to accept it. But the problem, practical problem is not that. Practical problem is that the specifications of the desired filter are given to you, a band pass or a band stop filter for example. So, what you have to do is convert these specs to that of a normalized low pass filter, design the normalized low pass filter, and then by frequency transformation you go to the band pass or the band stop or high pass filter. Do you understand the steps? Steps would be specifications of other kind of filter OKF, from which you go to specs of normalized low pass filter, then design NLPF, then use transformation to get H of the other kind of filter as a function of small s. Transformation is capital S equal to some function of s, small s. These are the steps. Okay. And in the case of high pass filter or a denormalized low pass filter, there is no problem. In the case of a denormalized high pass or low pass filter, there is no problem, because 1 radian per second you are going to make it omega p. All other frequencies shall be either multiplied by omega p or divided by omega p. In high pass filter it would be divided. You understand this? Why? No? Because the transformation is capital S equal to omega p divided by S. So, if you have a low pass filter 1 radian per second, and let us say the normalized low pass filter has a cutoff edge, has a stop band edge at omega S, then what would be the high pass filter? High pass filter will start at omega p, its stop band edge would be what? Omega p divided by omega s, or is it the other way around? Capital S equal to j omega s is equal to omega p divided by small s, right? And therefore, small s equal to minus j omega p by omega s. That is it. It will come automatically. For normalized low pass to denormalized low pass, it will be multiplication, but here it would be a division by omega s. Okay? In the band pass and band stop, however, because the specs may not satisfy this equal to omega naught square, may not satisfy this, you will have to make adjustments, and this adjustment I think we shall leave it for the next class.